Everybody, this is the International Space Science Institute's Game Changer seminar series, and where we look at missions that changed the game in planetary science and exploration. I'm Tilman Spohn. I'm your host here at ISSI in Bern in Switzerland. In the previous two seminars, we've looked at the exotic worlds of Itokawa, Ryugu, Pluto, and Charon. And if you missed one of these talks, they are still available as recordings on our website. The next two seminars, we will be looking at our neighboring planets, Mars and Venus, and the two ESA sibling missions, because they basically use the same spacecraft bus, MEX and VEX, or Venus and Mars Express. We will start today with Mars Express, and our speaker will be Ralf Jaumann, the principal investigator of the HRSC, the High Resolution Stereo Camera, a novel instrument at Mars, and still is, I believe, now at the Free University of Berlin. Ralf, it's all yours.
Okay, good evening, and thank you for the introduction. And Mars Express is a mission which operates at Mars for the last 17 years and hopefully for a few years more. But let me start with a simple story about Mars. So there was in 1888 the story that there are channels on Mars, and most of this is coming from an Italian observer, Schiaparelli, and he gave an idea to an American, it was a businessman, Percival Lowell, and he was completely convinced that there is life on Mars, there is water on Mars, and that was the beginning of the story about Mars and about exploring Mars. And Percival Lowell founded an institute and a telescope in Flagstaff, Arizona, and he, until the end of his life, he was completely convinced that the channels on Mars has been man-made, or at least made by aliens, bringing water from the poles to the equator. And then in 1965, NASA started Mariner 4 and visited Mars by a flyby. And what you can see here was one of the first observations of Mars, and you see impact craters. It looks like the moon, and it was a little bit, let's say, boring and disappointing. Going into the story of the exploration of Mars, it started in 1965 with Mariner 4, it followed by Mariner 6, Mariner 7, by Mariner 9. Mariner 9 was the first good orbiter who really provided global data. Then the two missions, Viking 1 and Viking 2, two orbiters and two landers. One of the landers really was equipped in order to look for life on Mars, but that was not successful in total. And then, disappointing again, was under scientists and also with NASA for a number of years, from 1976 to 1995. But in the meantime, there was a lot of discussion of water on Mars and life on Mars. There was a discovery of meteorites which were proven to come from Mars. They showed some kind of features which might be microbes. Discussion is still going on, but this discoveries really brought the interest in Mars back to scientists and also back to NASA. And then they started in '96 with the Mars Global Surveyor and Mars Pathfinder. So that was the third landing. And in '99, two missions started, Mars Climate Orbiter and Mars Polar Orbiter, but unfortunately both of them failed. Then we had in 2001 Mars Odyssey, and in 2003 Mars Express, the first ESA mission, which is going to another planetary body, followed the same year by two very long-living rovers from NASA, Opportunity and Spirit. And then we had another NASA mission, another NASA landing in 2007. And still ongoing, we had the Mars Science Lab, Curiosity, which is still operating. We had an atmosphere and exosphere observation still operating, and we also have the trace gas orbiter from ESA, the second spacecraft from ESA to Mars, also operating. And we have InSight, which is on the surface, looking into the interior, looking for the heat of the interior and also for the seismic activity on Mars. And we had last month the launch of Mars 2020. With it rover, it's a Curiosity-like rover, but it's able to really collect samples. And so far we had a total of 46 missions to Mars. 23 of them have been successful and 8 of them are still operational. And there have been 14 landings of rovers and landers, and 8 of them are successful. And of course, I think 1, 2, 3, 4 of them are still operating. And the future plan is ESA will launch in 22 ExoMars. That's a more or less exobiology rover, which is also able to drill. And in 26, NASA will bring back the samples which has been collected by Mars 2020. Okay, coming to Mars Express, it has been launched in July 23. We arrived in Mars in December 23, and the first image we get was January the 9th in 24. So, and since then we had about 21,000 orbits, and we have a mission on extension which will end of this year, probably will be continue for another 2 years. The instruments are a high resolution stereo camera, then a neutral energetic atom analyzer, planetary Fourier spectrometer, a visible infrared mineralogical mapping spectrometer, a radar, subsurface radar, then radio sense, and an ultraviolet infrared atmospheric spectrometer. So the partners are from Germany, from France, from Italy, from Sweden. And the status is the instruments and the mission spacecraft, everything is operational. And what we have seen was Mars Express flying over Olympus Mons. Okay, I will start with one of the major objectives of Mars Express, and that was to look what is the surface doing for surface alterations. Is the surface changing? Can we see the history of the surface? And that usually means we look for volcanism, we look for tectonics, and we look a lot for erosion, which is related to water, which is related to alteration by water, which is related to ice. And we want to do this as a function of time. And among the instruments, the 2 instruments, the camera and the visible and infrared spectrometer are the main surface instruments. And I will start with this and show you some kind of outcoming of these 2 instruments. That first to explain how this works. So that's the stereo camera, and the stereo camera is a scanner. It scans the surface, makes about 5 observations of the surface simultaneously, which means we have about 5 viewing angles, and we have about 4 colors. And we have strips which are in the order of 1,000 kilometer by 50 kilometer. The goal here is to put all these strips together and make a global mosaic. And we are still quite good in doing this. And here is an example of a surface area where we did this. And many of the strips in this area, we had about 60 to 80 of these strips with different colors and with different viewing angles. And what you can see here is what outcome out of this is a color image. It's an image of the surface, and it's also a digital terrain model. And putting this together, you can really fly over Mars. And that's an area of Mars where we had a lot of outflow channels, means a lot of material which has been, a lot of water which has been flown over the surface very quickly and damage the surface really by water erosion. If we look at the seasonal cycle, and that was one of the first things we did together with the camera and with the spectrometer. And what you can see here is on the left side, we have the South Pole. On the right side, upper, we have an overflow over the North Pole. And if you look at the image beneath this, you see the white, the grayish and the reddish areas. And if you look into the spectrometer information, then we could really see that the white is CO2 ice, and the grayish area is water ice, and the rest is dust on the Mars. And that first time showed that we have on the polar regions first stratified areas where we have a lot of dust in different layers, and then we have H2O. And on the H2O, we have the CO2 ice. So we have a real cycle. The ice is freezing in winter and the ice is melting in summer. And first is, of course, water ice freezing. And if the temperature goes down, the CO2 ice is also freezing. And that can also be proven if you look at different seasons. And what you can see here is an impact crater. An impact crater in the image A, it's let's say summer. Then we came to early fall, and then in C we came to later fall, and we see that we have some kind of frost on the surface. And the image below this frost image shows you the atmosphere and the saturation of water vapor in the atmosphere. And at a certain point, you get supersaturation. So that means the atmosphere is completely saturated and you get snow out of the atmosphere. And that's the reason for having the frost in this impact crater. The second discovery was by the radar instrument. And looking at the South Pole, the radar was able to really at least get a three-dimensional image of the ice cap, and finally got out that there should be something like an ice cap of about 1.6 million cubic kilometers. And if you spread this over the Mars surface, you get a global ocean of about 11 meters. So that was some kind of an estimate, which is very good and clearly shows and confirms, or has been confirmed by a lot of additional information so far. And then there was in 2018 a real lucky part of the radar instrument. At the South Pole, they really could find an area where they get a real strong radar echo. And this greatest radar echo that was so strong that it really suggests that we see liquid water in the subsurface beneath the ice. And that's a confirmation that there is still water in the subsurface, at least in the polar regions. And if you look at the area where we found this, it was not directly beneath the ice, it was in the wider polar area. And that means there's a great chance to have, at least at high latitudes, groundwater. And that's very interesting because that's good information that groundwater probably will host some kind of life. Okay, the next thing was to really think about the geologic history. And usually you look at the surface, and what we see here is the surface of Mars. You see valleys on the surface. You also see impact craters, and you see a lot of infilling in the impact craters. So there was a lot of geology going on here. And in order to understand what happened in these areas, or at least not all of the areas of Mars, you want to know when some geologic process happened. And usually you use crater counting, and I make it very simple here. So if you have a lot of craters on the surface, you have an old surface because it was long exposed to space and to all the asteroids and comets hitting the surface. If you have less craters, the surface is younger, and if you only have a few craters, you have the youngest surface. Okay, what you do here is you look at the diameter of your impact craters, the smaller ones, the larger ones, and you look how many of these impact craters you have. And then you get a distribution, the frequency of your impacts, and also the size of your impacts. And this can be used in order to estimate the age. That has been developed for the moon. On the moon we have, or from the moon we have samples, and these samples has been used to absolutely calibrate these impact curves. Okay, the next step was to really look at different geological units on the surface, and that is a map, a geologic map, and you see there are different geological units. The next step is to look at all of these different units and the ages, and make a lot of this crater counts, and finally you end up with what you can see here is a number of papers, all of them coming out of Mars Express, and showing different surface units, volcanic, tectonic units, fluvial units, glacial units over time. So over time means from 4.4 billion years to today. And what is here real visible, that was the situation we had before Mars Express, and what you see behind this, I will talk a little bit more, because that's mostly discoveries of Mars Express. And I will start with the history of the volcanism on Mars. The first story of this was volcanism on Mars is very old. We know that there are ancient highland prateras, means a specific kind of volcanoes, and what you see are different of the kinds of these volcanoes. Here's Olympus Mons, that's one of these prateras. Prateras are not high, but very widespread, and that's a small volcano on Mars, and that's a caldera on Mars. Okay, and what coming up here is that the highland volcanoes, of course, are very old, because they are in the oldest regions. They are now younger than 3.5 billion years. But if you look at the large shield volcanoes we see on Mars, like Olympus Mons, we really can see that the ages are getting younger and younger. And we'll start a little bit with this. Olympus Mons is the largest mountain in the solar system. So it has a base of 600 kilometers. There is an overlay over with Germany. So whole of Germany is covered by Olympus Mons. It's about 21 kilometer high, and it has some kind of a scarp here, which is 8 kilometer high too. So this volcano has to operate a long time, and it was not clear when it stops to operate, but HRSC was able to look in the calderas. That means the holes where the lava is coming out, and we found a number of different calderas, with the youngest one of about 100 million years. So that was the first proof that Olympus Mons at least was active until 100 million years ago. But even more, if we look at the flanks of Olympus Mons, we started to see some kind of lava flows which are much younger. So in the meantime, there are lava flows which is as young as 10 million years. So that means the volcanic activity is going on at least for the last 10 million years, and probably it's not clear whether we do not have volcanic activity today. Another point is the tectonic, and we know that the tectonic is mostly related to the volcanic activity. The tectonic is usually completely old. It's 4.4 billion to 3.5 billion years old, and it's a reaction of the volcanic activity, and this can be shown very clearly here. So on this side, you see a lot of extensional tectonics, because the volcanic activity is going up in a hotspot, in a very large hotspot called Tarsis, and on this we have the largest volcanoes. And if you destroy the crust by putting more and more magma and lava into the crust, there has to break. As Mars is a sphere, so in other areas it has to contract, and that's what we can see here very clearly. Another issue for the tectonics is the first building of the southern highland and the northern lowlands. But the most tectonic related features are due to the volcanic activity on the surface. And that means if you look at this, we really can see that the volcanic activity not stops at 1 billion years ago, or probably 3 billion years ago, as mentioned before. So Mars Express really could show that we have young lava flows which are close to 1 million years. And we even see some tectonic activity, which is also very young. So that basically means we have features on the surface which are much younger than we expected at the beginning of the exploration of Mars. Okay, the next step would be to think about water on Mars. There's a lot of discussion about this. Here, just showing the physical conditions, and the physical conditions is the phase diagram of water. And we know on Earth we have a very fine situation. Our temperatures are between 0 and about 50 degrees, and our atmospheric pressure is 1 bar. So we are in the liquid area, and on Earth we can have H2O in all 3 phases. On Mars we have an atmospheric pressure of about 6 millibar, and that's very close to the point where we have the triple point of water. That means below this you can only have ice or sublimating, means vapor, and no liquid water. But Mars has high mountains and very deep valleys. So if you change a little bit of this 6 millibars, you go to 10 millibars, then you get it liquid. So the deeper areas on Mars probably can have liquid water today. Okay, but we have a lot of features which really show that there was erosion by water on Mars. And a few of them, what you can see here is Hephaestus Valley, and that looks very great. You have a plain. The plain has been cut by a river, and you can see the river here. The river has been hit by an impact, and the impact you can see has some kind of a specific ejecta, which really shows that this ejecta was not thrown out ballistically, but it was thrown out like a mud stream. We also see very large outflow channels. What you see here is that's going from this point to this point of about 1,000 kilometers. So that's real flooding events which happened on Mars. And we also see a valley here, and within the valley, I come to this a little bit closer, we see a river. And we also see deltas on Mars. So there is a lot of information about water, and one of this information was in this river system. And this river system, you can see here, starts in a mountain area beneath some kind of basaltic layers, and it goes through very old highland, and then it gets a little bit weaker here, and you see it comes back here very clear and goes along here. And when you look at the H's, then it becomes very interesting. So we see that the lava, which is covered here, is about 3.3 billion years old. We see that the valley downstreams is even older. So the lava has covered this source region of the valley later than the valley has been operating. And then we see a young lava stream coming out from here, going here and covering the valley completely. But the valley was active after the lava took place by 1.3 billion years, and again graved into the valley, into the lava, and it always followed the same structure. So that basically means we have an active valley system for 2.2 billion years. It was not active every year, but it was active all the time. maybe there have been intervals of about a million years or 10 million years, but the water was on the surface at least until this 1.3, 1.4 billion years. We also see deltas, and that was the reason to think that there are impact craters where we see deltas coming into the impact, valleys coming into the impact craters. We see the delta here even better. And that basically means that we had standing bodies of water. And looking at some of these deltas, that's another delta. They are even young, relatively young, 1.5 billion years. That's younger than many of the volcanic activities. So that means the water was active on the surface over a long time on Mars. And if this operates, that was one of the ideas, and say if you have water on the surface, if you have standing body of water, then the water has to react with the rocks. And if water reacts with the rocks, we call it weathering. And if you put a basaltic rock into water, you really end up with clay minerals. And that's what you can see here. So what we see here is that alteration products. And if you get closer to this, you really can see that these alteration products are layered. So in this kind of layering, you only get if you have a standing body of water, if you had material which has been swept in this standing body of water, and then the water evaporates and you get some kind of this very clear and fine-scaled layering. And the same can you see here. I come to this a little bit later. And if you look at the spectral information of this, you really can see that you have a lot of different minerals, which are clays, which are salts, and all of this are, of course, weathering products. And if you look into one of these areas within the Valles Marineris, and these mountains here are all layered. You can see it here. And if you look at the spectral information, then we really see at the basis of these layers, we see clay minerals. On upper of this, we see some kind of sulfates. And if we go higher, we see more sulfates. So that basically means at the basis, we have clay minerals. And then we get salts. And if you have water, and if you have a weathering in water, and you build clays, then your water is neutral. And if you start to deposit salts, then your water gets salty and acid. And there was a study about this, taking all the images, all the data we have from Mars Express and also from the Mars Reconnaissance Orbiter, and you really can see there is a lot of different materials on the Mars. We have everything. We have phyllosilicates, means clay minerals, and we have a lot of salts, and we have different salts. And if you put this information together with the three-dimensional information, then you get a real good indication what causes the weathering. And we start here. So what we see here is the different colors you have seen before, different materials on the surface, but on a topographic model. And if we go closer, then we really can see that some of these areas have clays. So that's what you call smectites. So that's iron and magnesium. Then there are some clays which are aluminum rich. And we have carbonates. We really can see some carbonates. Then we see some kind of silicium, and we see salts. And when we start to identify this, then we really can see here we have some kind of a hydrothermal alteration, because that's an impact crater. So the impact induced heat make some alteration in this area. The second is what we can see is we have some kind of alteration due to the CO2 in the atmosphere. So that means alteration which really make the carbonates using the CO2 out of the atmosphere. And on the other hand, we have some kind of, if you put material on clay material, then you get a certain clay mineral, and that's the aluminum smectites, and that's some kind of a diagenesis process. That's burial of material, and the weight of the burial of the overlaying material really pressed the other material and induced some kind of alteration. But you can have the same alteration if you have some kind of rocky material and put in heat. And so here we know that was covered by material, and here we know it's some kind of a avalanche. So it means mass wasting coming out from the mountains, and the both is the same express. And finally, you really can see that the chloride salts are part of a lake which has been evaporated. So the whole story comes together if you put all the information you have together. And that finally brings you to the point that you really can see, we can estimate how much water was at what time on the surface. So that's the early Mars time. Here we have the mark of 3.7 billion years. And then the water is going down. So Mars is drying out. On the same story, we can see that we have in the early time, Neogen is the first epoch on Mars, we have a lot of clays. So we have this situation where the weathering really make clay minerals. And then at a certain time, mostly in the order of the change between Neogen and Hesperian at 3.7 billion years, we see more and more sulfates. And then finally, at the end of this, we see the oxidation of the Martian surface. That means basically we see the oxidized iron, and that makes Mars red. And most of this has been come out of a lot of publications from Mars Express. Basically, it means we start by a neutral alkaline situation at the beginning of Mars, and then the geology of Mars and the water-related geology of Mars getting very acid. The question is still open where all the sulfates are coming from, but it's probably a question of reducing the atmosphere and also stronger input of sulfur by the volcanic activity. Okay, in total, if we look at the history of this, we know we have a lot of water at the beginning of Mars, but nevertheless, there is water-related surfaces which are as young as some kind of 10 million years. So there is something going on the surface, at least in younger Amazonian times on Mars. That basically means that's one of the discoveries of Mars Express. And finally, if we look at another process on the surface, which is glaciation, that was also very interesting. So we have ice on the poles. We have already seen that we have ice, means frost and snow in the northern and the southern higher latitudes. But, and that was really surprising, we start to see at Olympus Mons, and Olympus Mons is in the lower latitude, so it's very close to the equator. We see what you can see here, that's some kind of a block glacier. What we see is the material, the rocks, which has been transported by the glacier. Here you see one of these tongues, and here's the other one. We don't see the ice anymore. We are not sure that the ice is not still beneath this, but we see the material which has been walked or has been moved with the ice, the rock, and you see the striation here, and even more closer to the equator, that's an impact crater, that's a mountain. The mountain is about 3,000 meters, and there is some kind of a car region, so there has been ice there, and it flows down in the first impact crater, and that it overruns and flows in the second impact crater. So the ice probably is also still beneath there, but you really can see that there was an icy flow process on the surface. Here is an image of this impact crater. We flew from the other side over this mountain, and you really can see it's a glacial feature. There is no doubt. The material has been transported, and it has been transported by ice beneath of the rocky surface. Okay, if you look at this, we really see that most of these features occur at, let's say, mid-latitudes. And the important thing is, if you look at the ages of all of these glacial activities, we see it's very young. It's very late in the Martian history, so it's very young. And that is another issue which is very interesting. So most of these features we can really see. That's a feature with a higher resolution than we have, but you see it's a glacial feature. That's glacial features as mentioned before. And there's a theory that the obliquity of Mars is changing. So Mars doesn't have a moon, so its axis will change its inclination. That can be changed up to, let's say, about 50 degrees. And there is some kind of a variation in this. So if this happens, and if you change the axis of Mars, which is today something like the Earth, 27 degrees, to about 40 degrees, you will get melting of the poles, and you will get the ice close to the equator. And if you get the ice close to the equator, you should have been there glacial features. And we have a lot of glacial features here. So that was Mars Express found these glacial features and these glacial structures, and that really confirmed the theoretical model of the colleague Lascar, which proposed that we will have this inclination changes. And that basically means climate changes on Mars. And that's on a high frequency. So if you look here, so that's a frequency of about 100 years. And the higher frequency is about in the order of 5 million years. Okay, and that clearly shows all of the measurements we made that we have glacial activities that shapes the surface, and it's probably active today. So Mars is not as quiet as geologically quiet as expected. Okay, what does it mean for the climate on Mars? And that's not the whole story, because currently we know Mars is cold and hyperarid with annual surface temperatures which are mostly below 0 degrees, a lot of below 0 degrees, minus 60 degrees. So the temperatures on the surface are in the order of minus 100 to probably at the equator sometimes 20 degrees. And we have a very dry and a very thin atmosphere, a dry and oxidating surface, and liquid water is on most parts of the Mars not stable. Okay, during early Mars, that means 3 billion years ago, the sun was not as hot as today, and it should be also very cold. We are not sure. So the question now is, how can we explain this? And there is an explanation that has greenhouse warming. Another explanation is at the beginning we had very many CO2 clouds, and that basically means also greenhouse warming because the sun is not coming to it. There are large meteoritic impacts. We know this. We see all the large impact craters. We had an area of sulfur dioxide emission from volcanoes, which also reduce the surface temperatures. And we have local snowmelt due to obliquity and eccentricity variations. So that's what I showed before. But the question is, we see a lot of liquid water on the surface. We know that this liquid water has to be stable on the surface for some time. We see this water in standing bodies of water, large crater lakes and the valley networks. So that basically means we had a warm and wet Mars because the water has to be stable. But there's no evidence that the Mars was at the beginning at least warm. In the meantime, we have seen that the glaciers can do a lot of job of erosion. In the meantime, we also have seen that the activity of the water can also be related to climate changes by changes of the inclination. So we can also have cold and wet early Mars, and we probably could have a cold and icy early Mars, because all of the surface features we see, they are not related to annual processes, but they are related to long-lasting processes, and most of this may be the change of the inclination. It's still an open question. It's not clear how dense the atmosphere was at the beginning. It's not clear how warm Mars was at the beginning. So that's still an open question. Okay, and there is another issue. We know that Mars has an atmosphere. I told 6.1 millibar pressure. It's not very much pressure, but the atmosphere is still there. You can see that's a limb image of Mars Express, and you see really there is atmosphere over the limb. We see a lot of dunes. What you can see here are dark material dunes, that volcanic ash dunes. And what you can see here is an HRSC image. HRSC is a scanner, and we have a forward and backward looking channel. And what you see here is that you have dust devils, that some kind of a very intense vortex which took the dust into the atmosphere, and you really can see a lot of them here, at least 5 of them, and they are moving, because we can really measure with forward and backward looking that they are moving, and that's the part of a cold front which is going over the surface. What you can see in this point is the volcano RC Mons, and RC Mons has what you call an organic cloud. So it hangs on, the cloud hangs on the high volcano, and the volcano is about 23 kilometers high. Okay, here again is the orographic cloud. It's really hanging on the volcano itself. Here we see some kind of dust storm on the North Pole area, and here we see, it's not hard to see, but we see a lot of atmospheric clouds on Mars. And what we see here is the density of the clouds, the number of the clouds measured mostly by the Omega experiment. And you can clearly see that they are distributed very broadly, but mostly in the area of about 45 to minus 45, or 45 north to 45 south. And most of the clouds appear in, let's say spring and summer times, and then they disappear in the winter times, because the material in the winter times, which is in the atmosphere, freezes out at the poles. Okay, and we also see dust storms, and that's from this year. That's an observation from May 22 to June 10th, and we see in the South Pole area, we see the development of a dust storm, and you see that a little bit dust here, then the dust is getting larger, and then the dust is moving to the south, and here is some kind of an inlet of these areas, and you see here the first dust covering, and then you see that some kind of a cyclone which is taking dust from the surface, taking also CO2 and water vapor from the surface, and this kind of dust storms are moving over the surface, so you really see surface of the Mars and dust which is running over the surface, and that's the front of the dust storm. Okay, so many observations of dust accumulation and dust storms and dust devils give some hints for the speeds of the atmosphere. And what you see here is a measurement also using the forward and the backward looking channels of HRSC. And if you look at the time delay and the distance, which we make here, then we get the speed in meters per second. And of the observations you see here, we get for this dust movement about 26.6 meters per second. That's not too much, but it's good enough to move a lot of dust around. And another question is, how long can this dust material in these dust devils exist? And here are a number of observations. And the observation here is clearly see there is the track of the dust devil on the surface. That's the actual dust devils. And here we see that it decreases and shrinks very soon down. And it depends on the size of the dust devil. So if there has a diameter of 1 kilometer, they exist about 26 minutes. And if they are larger, then they exist more than an hour. And some of them are so large that they really get up to 40 kilometers high and exist very long and can develop to a real dust storm. And that the dust, the atmosphere affects the surface can be seen in this image. So that's one of the impact crater, and this dark material in the impact crater is something like that you see on the image on the right side. So that's dark material, which is very fine. That's volcanic ash. It has been put together by the wind to dunes. And here you can see an observation in 2005. This material has been within the crater. And if you look at the same observation in 2008, we really can see the crater is clean and the material, the dark material, has been thrown out of the crater and covers the area around the crater. So the dust is today still able, the wind is today still able to move a lot of dust. And here again, a number of observations of this. What is really interesting, number of observations which are coming mostly from Mars Express, and it really clearly shows that we have some kind of dust uplift by dust devils, which is in the order of very small ones and larger ones, which are the order of a kilometer and more, and they go up to about 4,000 meters high, and they get speeds which are in the order of a few meters up to 60 meters. So that's the limit which material can be transported on Mars, but it's good enough to build the dunes. It's good enough to even operate on Mars and probably do also some kind of wind erosion. And there was a story of what we know about methane, and what I bring here to your mind, the first discovery of methane was by Mars Express, but it was long debated. And in the meantime, the debate, it's clear that we have methane, and we see methane in the atmosphere. That's this area. And here we have the Gale crater. And there was an observation in 2013. And there was an observation that Curiosity really discovered in Gale crater very low amount of methane. And one day later, Mars Express started to see this in the atmosphere. So there's a combination. We know it comes from the surface and we know it's in the atmosphere. So in methane is still a story. It's a question. Methane has to come from the subsurface. And there are probably two possibilities. One possibility is of course, life. We are doing this, and probably some kind of microbes on Mars will do this too. But the other possibility is also that weathering of rocks, and if you take an olivine rock, it's a certain mineral, and put it together with water and wait some time, then you also generate methane, CH4, and that finds its way through the surface. Through the crust, and it even finds its way via cracks, or it's probably stored in the permafrost, and when the permafrost starts to melt, then it gets to the atmosphere, and that's what you can measure in the atmosphere. So it's an open question where it's coming from, but there are two clear reasons. There has to be water in the subsurface, otherwise we don't see the methane. Okay, and at the end, I will show you some kind of a curious thing we discovered with Mars Express. That was one of atmospheric observation. We make for atmospheric observation global images. So we look from one side to the other side of Mars. What you really can see, there's Olympus Mons just for orientation. What you really can see, we have a cloud. We have a cloud of the surface of Mars. But we also see above this cloud, we see this. And we have really been amazed because that was a very strange structure. It's not a cosmic hit, I'm pretty sure. So we are still debating, but I'm pretty sure. The critical thing is it was about 20 kilometers from Mars Express, in a distance of 20 kilometers from Mars Express. So if it's not whatever cosmic hit error, then it could be another spacecraft. And we started to look into the spacecraft. We know that there are a number of spacecraft active on Mars. We know their orbits, so they are not of risk. But there are dead NASA orbitals. That's Viking 1, Viking 2, Mariner 9, and Mars Global Surveyor. There are even the same number of dead Soviet orbitals, Mars 2, Mars 3, Mars 5, and Phobos. So we asked NASA, because we had our position at this point from Mars Express, we now asked NASA, we now asked Roscosmos, and figured out that nobody knows the orbit of this dead spacecraft. So that means the orbit of Mars has some risk. And if this was true, what we saw here, 20 kilometers away from us, so then it was a critical, let's say, critical distance. And there are still some unknowns in the Martian orbit. Okay, so that's most I had to tell you. And what I want to show at the end is, and take a few minutes in order to enjoy, that's a flyover Jezero Crater based on the observations of Mars Express. And you know, Jezero Crater is the target for the Mars 2020 mission and the Perseverance rover. And what you can see here, we're coming from the south, we clearly see that there is an outflow channel. So that's an impact crater we're flowing in, and you have seen the outflow channel, and now we flow to the northern part. And what you really can see here is we have an inlet channel and we have a delta, and Mars 2020 will land close to this delta, and the rover will explore the delta and will save sample areas within this delta, because we know that there are a number of these weathering products I showed you. There are carbonates, there are salts, and there are a lot of phyllosilicates. Okay, then thank you for your attention.
Thank you very much, Ralf. This was very interesting, in particular that spacecraft you saw there. Have people suggested that it's an alien spacecraft, maybe? Well, just kidding. But before I start the discussion and ask Saliba about raised hands, just for clarification, when you speak of wet and cold and wet and warm, can you give us an idea about the difference in temperature between those two? I mean, wet and cold still means that you're above the melting point of water, aren't you?
Wet and cold means, yeah, that cold means really freezing. Probably not all the year freezing, but most of the year. So what we know from permafrost areas on Earth.
Okay.
Okay, and if I say cold and icy, then we means annual temperatures beneath freezing. But we know also from Earth that beneath an ice cover, you can have liquid water.
Sure. Okay, thank you very much for that clarification. Now, Saliba, do we have raised hands? People?
Yeah, we have two raised hands. The first one is a name, well, it's actually some letters, but it starts with DCT. So if you can hear me, I am asking you now to unmute your microphone, please, and go ahead and ask your question.
So PCT.
DCT.
DCT, okay.
Yeah, it seems.
Oh, this, okay, this is a very complicated name.
Yeah. Okay, so we go to the next one. There's Jose Juan. If you can hear me, can you please unmute your microphone and go ahead and ask your question? Jose?
Oh, yes.
Yeah, okay, go ahead, please.
Well, yes, my question was about the methane. You know that already ACS and NOMAD has shown with more than 30,000 profiles that there is less than 0.05 part per billion in volume of methane. This is 100 times less than the published measurement. And I think that the measurement that ACS and NOMAD that are compatible with zero methane in the atmosphere, as all the other measurements already taken. All the measurement taken and published are compatible with no methane at all. PFS was designed to see methane if there was a lot more than it was, because there was the sensitivity of PFS to see methane was,
yeah, please. I mean,
2 or 3 orders of magnitude less.
I think we got your point. Yeah.
Okay, thank you.
Yeah, Ralf, you want to answer?
Yeah, I think we had this discussion many times. I'm not the expert on this, so probably I can ask the PI of PFS. But on the other hand, there is also a measurement which is coming from Curiosity and directly from the surface. So I don't know. I'm really.
Yeah, but the measurement of Curiosity, when Curiosity in the first 3 years saw no methane at all in Mars, it started to see methane from time to time, and nobody knows the origin of this methane. Probably the same Curiosity produced the methane that is measuring. If they are measuring methane and there is not something broken in their detector, that is probably the best solution, because in the first 3 years, all measurements of Curiosity were negative, as all the measurements done up to now are compatible with nothing.
Okay. So,
sorry.
Yeah.
I know, but there's also an issue with Maven. So as I remember, Maven was not able to see methane, but Maven has a different orbit. So, but I'm not an expert, so
okay, no problem.
What I showed you is a publication, and the publication has been reviewed. So,
yeah,
we have more questions. No, thank you. Now we don't want to get this into a debate on methane. I mean, that is a different story, I think. We have other questions here in the Q&A section that are written questions. I can read them to you. So Andrew Ball is asking, thank you, Ralf, and asking, were operations of the HRSC super resolution channel completely stopped, or is it still used from time to time?
Oh no, it's not completely stopped. We still have a resolution problem, and that's temperature dependent. So we operate the SRC and we use it when the data are very good. So we cannot control the SRC temperature. So we can just do it by chance. But we have a number of SRC images, and we probably use it. We use it mostly for Phobos. I didn't talk today about Phobos, but there are two reasons for this. We get highest resolution at Phobos, and when we observe Phobos, then the instrument is colder than when we observe Mars. So I would say that the scientific outcome of the SRC is mostly observation of Phobos at highest resolution.
Okay, Sasha Heupel asks, thank you. Well, first, thanks for the amazing, interesting talk. But if you could put a rover on Mars at your position of your choice, where would you put it?
That's always a good question. So it depends. I am a geologist, so I usually would put it in some areas where we really see a lot of these alteration products. But all of these areas so far, besides Jezero Crater, they seem to be a little bit difficult. So I would go into Valles Marineris and certain areas in Valles Marineris, but I'm pretty sure that no engineer would follow me.
Ariel Ladegaard asks, when Mars Express received its mission extensions and assuming it's in good health, are there any key observations or scientific campaigns that it will focus on in the time ahead?
Yes, we only get extensions if we have good ideas. And there are a number of comparative observations with other spacecraft. And that's one of the reasons. The other reason is Mars is a very large object, and one of the goals was to have global coverage, and one of the goals was also to have observations with Omega at mostly different areas. And the resolution of these instruments, including HRSC, is in a way that we need some time in order to get the highest or the global coverage out of this. But there are a number of other things. So there is some correlation with the Trace-Gas orbiter. There is some correlation with MAVEN, because all of the exosphere and atmosphere observations, they are some kind of in situ observations. They get a very short point of observation, and you need different orbits in order to make very clear environment observations of Mars. And Mars Express has a very eccentric orbit, and Mars Reconnaissance Orbiter and TGO has a very circular orbit. So in order to understand what's going on in the atmosphere of Mars, you need these different orbits and you need the different instruments. And that was one other goal why Mars Express is still in the game.
Okay, I have two questions that are kind of related. I mean, one is asking about the water underneath ice features that you mentioned, and the question is, why cannot Mars resolve this uncertainty? And the other is, I mean, if ground radar would show us water, could ExoMars drill and find the liquid water at the bottom?
That's good questions. So the first reason is, if you have water under these glacial features, the water or the ice is not very thick, and Mars will have a problem. So they need, in order to get the signal, they need at least whatever, a few tens of meters of this. And I don't think we have this. And on the other hand, we don't know how deep the ice is under the glacial features, but I think it's more than the few meters ExoMars can drill.
Okay, Hans Sineker, wants to know, I mean, what could be learned from a manned mission to Mars?
Oh, that's a very good question. And I'll come back and say I'm a geologist, and I was involved in one of the first rover missions of Pathfinder. And simply, we learn a lot from the rovers, but when we are sitting in a room and discussing what the rover should do the next day, and having the rover doing the next day, every geologist, not the engineers, but every geologist had the feeling, and me too, give me an hour, a hammer, and a magnification glass, and I will do a better job. So that's what I will say. For the current time, human beings can do much better than robotics.
This is a question I think you can answer. Eva Stücken, how much of Mars surface is exposed bedrock and how much of it is covered by sediments?
Oh yeah, would be happy to know this. But I think it's something like Earth. Yeah, we have on the Earth a very thick crust, and we have some sediment. I don't know the ratio on Earth. Probably you know it, but I think it's almost all is bedrock, and you have about 10–20% sediment in total.
Okay. Pavel Krupa wants to know, is there a connection between the early-born Earth and early-born Mars and the faint early Sun?
The only connection I can see is that when Mars had his big problem changing from alkaline to acid conditions 3.7 billion years ago, on Earth, we really see the first life. So I don't know what happened at this point, but there was a clear climate change on Mars, and we don't see this climate change on Earth. I'm not really familiar, but I know that we had also a very cold Earth at the beginning, or at least phases of very cold Earth at the beginning.
René Dufat, I hope I got that right. Can the water on Mars be exogenous, coming from comets or asteroids, for example?
That's a good question. We have the same question for the Earth. So we don't know where the water on Earth is really coming from. It can be, yes.
Okay, then the next question I can answer. Leo Enright, and maybe others want to know that too. When can we expect the video of this superb event online? Tomorrow, next week? Well, today, actually. I mean, we'll probably put it, online today. At least we did so in the past presentations. We had them online the same day. Thomas Früh wants to know, do we know what exactly is causing the dust storms? What is different from the normal energy budget of the atmosphere?
I think it's mostly temperature. And that's the reason the dust storms really start in spring and evolve in summertime.
Okay.
And
the next question. Sorry.
Of course, there's also a reason is the topography of the surface. So we have much more topography on Mars than we have on Earth. And as I showed the orographic cloud, we also have orographic clouds at Olympus Mons. So that basically means you have some kind of mist tails within the circulation of the atmosphere, and that probably produces vortexes, and that probably starts some kind of larger dust storms.
Okay, I have one last question here. Oh, I got one more, but okay. If one were located at the surface of Mars and looked up to the sky, could one observe EUV and X-ray light for stars and other objects? At Earth, we can not see this light as it is absorbed by the Earth atmosphere. So would the Mars atmosphere be transparent for this light?
I know that all of the landers had done this. Though they are able to put their cameras on the sky and they really observe at least stars.
I wouldn't know, actually. Yeah. And I think that is now the last question. Thanks, Ralf, for this exciting talk. Do you think that subsurface liquid water might be localized even today in equatorial regions and being the origin of the exposed clay minerals like smectites?
At least OH is is stored in the clay minerals, a lot of them. And if we talk about some kind of sulfides, so a lot of water can be stored in sulfides. But I'm pretty sure that if we go to deeper regions, that means Hellas Basin, yeah, minus 10,000 meters below the 6.1 millibar. So we are in the order of about 10 to 12 millibars. And then, of course, I'm sure that there can be liquid water even today.
Okay, keine offenen Fragen, so no open questions anymore. Thank you very much, Ralf. This was most interesting. We had 160 participants in the seminar. I just wanted to advise you that next week we will be having the Venus Express mission introduced by Anne Vandale from Brussels. She's an expert in spectroscopy, and she will, introduce Venus Express to us and tell us what changed the game about Venus, from that mission. So I'm looking forward to seeing you all back again next week, and have a good day and a good week. Thank you very much. Bye-bye.